that we have. And I think you all have attended the microprocessor course. And if it is 8085 microprocessor, you might have recalled, you may recall that there are registers like B, C, D, E, H, L, which are general purpose registers. And these general purpose registers, these GPRs, are accessible by the user. I mean, you can easily access them in your code. In 8086 also, you can access them because they are actually used during a computation. If you add something, so the result will be stored, and you can store some values in B and some values in C, like that. So these are general purpose registers. These are user visible registers or user accessible registers. User can access it through its program. Although in a C program, high level program, we don't directly access the registers, that's true, but internally, when it is implemented, when it is converted to machine code, these are there. Okay. And in addition to that, there are some stack pointers. Stack pointers are pointing to the stack. So again, while dealing with memory management, you will learn more about it. And just to mention, in a typical Linux uh, philosophy or a Linux design, or I mean Unix type system design, there are two types of stacks maintained. And if you can recall, in the last semester when I taught the uh, OOPS class, object-oriented programming, when I think of a program, when it is running, we have four segments: the stack segment, code segment, data segment, and heap segment. And the stack segment is a collection of locations which actually stores the local variables and say the return address of a function and all this. So this stack, which is a part of a program or a process run by a user, is called a user stack. Okay, so this stack pointer will point to the top of the stack. Okay, if there is a series of function calls, this stack is of use, and after the return of the function, after the function completes, from the stack it finds out where to return back. So this is the user stack we are referring. But in the Unix philosophy, uh, as we already distinguished, that there will be two modes of operation, two modes of running of the processes. One is the user mode and another is the kernel mode. So there will be two stacks maintained. Okay, so when the process is running in the user mode, it will be using the user stack, the one that we referred, as I mentioned, I referred in my previous course. Often we referred. So any recursive calls and all this. So in the user mode, it utilizes that. But whenever the control or the privilege or the system, I mean the process goes into the privilege mode or the kernel mode, it uses the kernel stack, or it sometimes is also called as a system stack. So there is a single kernel stack or a system stack which is used by the operating system routines and also uh, by the user programs or user processes when they switch to the privileged mode. So probably you are getting things, and the more will be discussed while discussing about the process management. So to summarize, when you talk about stack, then we have got two types of stacks. One is the kernel stack or the system stack, and another is the user stack. So kernel stack is just one throughout the system, but the user stack, as you know, I mean, as you can guess that if there are 5 user processes, so each user process will have its own user stack. Okay, so the stack pointer will point to the user stack, the corresponding user stack if it is in the user mode, or it will be pointing to the corresponding kernel stack or the kernel stack, system kernel stack. So this is an important register. But the contents of these registers are pretty much visible, and you don't have any privileged kind of action to be taken. So you are free to use it. However, there are some special registers, special purpose registers, which can be accessed by a user process only if it is in the privileged mode. So the operating system processes, they can access anything because it's written by the designer, and that guarantees that they are safe to use. But the user processes are written and developed by normal users who might be intentionally or unintentionally try to, say, corrupt the system. So that's why in the privilege mode, only in the privilege mode, these special purpose registers can be accessed. And this PSW, the program status word, it's a part of the special purpose registers. And there are a few more, like memory buffer register, memory address register, input output address register, input output buffer register. So these are something like when you perform a memory or IO operation. So these are the registers where the contents will be stored, and from that it will be passed on to the uh, then the CPU will access. And when the CPU wants to write something to the IO, it will pass on, it will first place it in that particular register, and from that it will be transferred to the IO. So there are few more, and again, as I mentioned, that these are some generic terms that we are using. So if you have 8086 or maybe 80486 or 586, Pentium machines or maybe ARM processors. So each of these, or a Motorola processor, each processor will have its specific register code. And if you are a designer, you have to know each and every details, the size of the registers, their purpose and all this, and you should know the names so that you can write the OS in details. But for us, we may be happy at this moment to know what thematically what it contains. And this PSW, program status word, uh, in a generic term, we can think of it as 5 type of registers. uh, so then the control registers, which stores, it's a set of bits. It is storing the outcome of a operation. If there is a overflow or a underflow or any such kind, then these flags are set. So there's a set of flags under this control code, and you cannot directly access, because if the user can access it, even if there's a division by 0, or there's an underflow or overflow error, it can set the bit to 0 and create problems. So even though the instruction is not correct, so the user can set it to correct. And these flags, once set, sometimes it informs the OS that something wrong has been done, and the OS takes measures accordingly. There is a mode bit. This is, as you can relate quite easily, that this mode bit is referring to whether the computation is done at this moment in the user mode or in the kernel mode, and accordingly the privileges will be offered. The memory protection information is again a set of, there may be 2 registers or 1 register and segment, offset. So this together defines the boundary of the locations, the set of the range of the locations that a particular user process can access. And if it goes beyond, there will be a segmentation error if it is not in the privilege mode. So this memory protection information, that also we mentioned in our last class. Then the interrupt mask. So interrupt mask, we'll talk about it in the next slide. So what is interrupt mask and interrupt code, we'll see that. And what is interrupt specifically, we'll see that in the next slide. Okay. But before we go into that, the interrupt, the mask, interrupt codes, and all these details, and we can also see that there are some interrupt lines here, IO interrupts. So the point is, if the IOs, input output devices, generate some interrupts, so they will just generate some signals in these lines, in these pins in the CPU, and the CPU will be responding. So before we get into the interrupts, as I mentioned, let us come across few relevant terms. The first one is preemption. So preemption is an important term in OS, which means it's the act of temporarily interrupting a task being carried out with intention of resuming later. So just ignore the definition. Simply putting is, say if I am taking a class, say for example, this class, although it's a virtual class, I have plans to continue it for 1 hour or maybe 45 minutes. But in between, there may be something that might stop the continuation of the class. What may be the reasons? I get a very emergency call from maybe from my family or from the HOD that something has happened, so you have to suspend it, and there is a meeting called immediately. So no matter what you are doing, you have to temporarily interrupt the task, means taking the class, and but although I am interrupted, what I know that I have to, whenever I take the next class, I have to start right from this point. So everything need to be saved. So preemption means temporary interruption of a current task, or a ongoing task, which we may need to resume later on. Now, if this happens in case of a class or a lecture, what we generally do, as you can see, these markings of these, pointers and all these markings also I need to save, and also probably I need to save the particular slide number. So as such, there is no tool these days which can save the status. If I want to save the status, the state of the virtual class, this is not possible. But this is important to save, because in the next time when I want to resume, I want to resume right from this moment. So what is this called is the state of the class. And in terms of the computation, we can think of the state of the CPU. So now let us come to the analogy of computation, that a CPU is executing a user process P1, and there are other processes which are also waiting to run, or they are ready to run. And these days, a computing system can accommodate multiple or more than one process simultaneously. But that does not mean that a process that is currently running will continue running forever. If I start the class, that does not mean that I continue taking the class for hours after hours. Okay. So there is inherently some reasons why this preemption is required in a computing scenario. One point is CPU preemption. Why it is required? Because you should give others also turn, so that they also feel that they are using the CPU, and that is how it is done. It is basically time shared. Our classrooms are also time shared, right? The LGC1 is used by me for 1 hour, the next 1 hour somebody else uses. So the same thing happens here. So there are several reasons why preemption actually is required in a computing scenario. And when the preemption occurs in case of a CPU or a running process, then we need to save the state of the CPU. What is mean the state of the CPU? As I mentioned, so whatever is the contents of the registers, this general purpose registers, the special purpose registers, everything need to be saved, because that is the kind of work that I have done till now. So I want to store those works that I have done, and when the same process is again loaded, or again it will get a chance to execute, it will just load the status and will resume from that same point. That is how this is done. So the state of the CPU is the contents of all the registers, GPRs, PSW, SPRs, and all. And this process of saving the context, saving the state of the CPU corresponding to a particular process, say A, which is running, and if because of some policy B is chosen to be uh, in the running mode next to A, so then we would have to load the state of B, CPU state of B, which we might have saved some time back. Okay, so this process of saving of the state of one process and loading of some other is called as context switching. Okay, because you are switching from the context of one process to the other process, like that. In case of class, you are switching from the context of a waste class to a context of a, say, database class, like that. So this preemption is an important term. Context switching is an important term, and to enable context switching, or a part of context switching, the state of CPU need to be stored. And it is not only the state of the CPU in terms of the registers. We'll find that few other things also need to be stored, that we'll see later in the process management topic. Okay, and in our class, in our physical classes, how do we store the state of the class? Generally, the faculty tries to recall, stores it in his mind. Okay, I have done this much. The next day the class starts, he tries to, I generally do, I just write the last class information, and from there I restart. So like that. So the loading and memorizing is just like manually. But in the system, you have to do this. So these are stored, and where these are stored? These are definitely stored in some portion of the RAM, So we'll see it later how it is managed, but this need to be stored. And this is not only the register contents, but few other things also need to be stored. Okay, so you can resume in a perfect sense. So these are the information related to the central processing unit. It's context switching, state, and all this. Next, as I mentioned before, going to the IO, because we have talked about the RAM, the memory management, we have talked about the related hardware for address translation, we have talked about the CPU, mostly focusing on the registers, and this IO is left. But before we go into the IO, as you can see that IO has got a interrupt, has a line towards the interrupt pin. So interrupts are important, and we should discuss first about the interrupts, a very basic overview of interrupts, and then we deal with the IO, talk about the IO. Okay, so what are interrupts in the OS? Again, this is a very simple definition. OS is primarily event-driven program and runs constantly and depends on events happening to execute them. We will explain this. Events happening to execute the modules. And what is an event? In a more generic way, you can say that event is any situation that requires the operating system's attention to be drawn. Okay. So the best analogy, I think, again from the real life, is when you think of the maintenance department of our institute. So what the maintenance department does, it has got mechanisms to repair, your electrical equipment that is there in the hostels or in our campus. It is also supposed to deal with any kind of maintenance in a civil maintenance or maybe scavenging and all these issues. But what they generally do, I mean, they basically monitor all these resources, all the resources belonging to the estate department is maintained by the maintenance department. But if you can, it is intuitively, it can be understood that they are basically an event-driven department. Okay, what do you mean by that? The event-driven means they don't have a routine work. So only if there is an event reported, they need to take actions like that. So maybe in the morning you report that okay, the power gone off in this hall 5, it's completely off, something went wrong. There is a report that there is a sparking or something short circuiting is there in some other residence, or maybe there is a blockage in the sewage system, so like that. So only if such events are reported, they will rush to the to take actions and all this. However, one fine morning, I mean, the whole day, maybe hypothetically, you can think of that nothing happened. So everything was fine. Maintenance, everything was fine. No electrical, civil, or scavenging complaints are there. So what the people will be doing, the whole department will be just sitting. Okay, they'll be sitting and they'll be just waiting because they know that they don't even care to ask that is there anything wrong, because the process is if there is something wrong, you'll be reporting that, and this reporting is something like the interrupt. So the OS designer, I mean the system, what it does, it associates an interrupt with each event. So here also you basically have to interrupt. How do you interrupt? Sometimes if it is truly an emergency, you make a phone call, that is through which you interrupt the department and you say that okay, I've got this problem, so you have to fix it immediately. Sometimes if it is not so important, like civil complaints, you just go there and feel asleep and then submit it. So that is how you interrupt them. So they will look into it and they will do it. But these interrupts, so corresponding to each event that might trigger or that might happen, maybe the maintenance department also has defined some interrupts, some precise interrupts, like fixing lights, fans, then these like that. And the point is, at the same time, they have also set some priorities, because now if there are 10 such events that has been reported and they have got only 3 persons serving them, so they need to prioritize it. I mean, they need to find out, and in many cases it will not be first come first serve, because if there's a short circuit case, that need to be attended prior to a simple fan repair. Okay, so in this case also, in case of system also, the interrupts need to be prioritized, and interrupts are indeed, the OS designer not only associates an interrupt with an event, but also it assigns priorities to those interrupts. Okay, and This interrupt is nothing but reporting the occurrence of an event to the OS and enable it to perform appropriate event handling actions. So what is event handling here? Event handling in a real case, it will be you are going and fixing the problem. Okay. So first of all, you have to find out what is the problem. If the problem is the light is not glowing, and maybe that you have to take a bulb, a fresh bulb, and you have to replace it. If the problem is because of the switch, you have to then fix the switch, but the light still glows. So like that. So to find out what exactly action need to be taken. Now let us, once the analogy is known. So the thing is, there are certain uh, departments or certain say areas in our real life which are basically event driven. But say for example, my class is not event driven. So this is a routine work. So I know that I have to take the class right now. So like that. So when you come to the computational scenario, there are classes of interrupts are defined. So this is again a generic set of classes. Again, depending on different types of OS, Linux, Windows, and the different other operating systems, they have got their own way of defining the interrupt classes. Now, these tables, these figures I have drawn, I've just copied and pasted from the Dhamdhare book. So you can just check that book, go through the details. It's nice to read the book, easy to read. So I would request you to just go through it once, and the PDF is available. I'll share it with you. Okay. So this class of interrupt is the IO interrupts. So what can be the cases? The conditions like IO has been completed, or some IO is malfunctioning, like printer. It was printing and then suddenly there's a paper out. So there's an interrupt that okay, there's a paper out, something like that. Timer interrupt. It is important because, as I mentioned, that CPU is just one or two, and there is a pool of processes or programs which are active in the system. They're trying to get hold of the CPU to execute their instructions. So the point is, without a timer interrupt, you cannot manage things. Like there are 3 classrooms, and we are having say 33 faculties. Say for example, they are all trying to get their classes done. So here the timer interrupt is the bell is ringing after every class after 1 hour. So a timer interrupt is important, which is raised at fixed intervals in case of a time shared system. We'll talk more about it later. Or it may be when a specified interval of time elapses. You set some time, it down counts, and when it reaches 0, you then take some action. But the most important thing is, so these are kind of hardware interrupts, IO interrupt, timer interrupt, these are kind of hardware interrupts. But there are another class of interrupts, broad class of interrupts, which are kind of software interrupts. Okay, these are program generated interrupts. So what are the purpose of this? So these, sometimes there are some exceptional conditions that occur. Exceptional condition means there is underflow of a division, or there is underflow that you are trying to add 2 very large numbers, which is not able to fit to the the register that is provided to you. So it will overflow, or maybe 2 small numbers. It may be that the memory protection is violated. You are somehow, your virtual address has generated address. Say for example, you have allocated some space in the heap, and you have assigned the base address, and then in a pointer variable, and then you release that free space. Now if you use the same pointer to point to that location, now you are trying to do something illegal, because you have not allocated it. So it might be used by some other process by the time in the heap. So the thing is, these are the cases which might trigger a memory protection violation. uh, I mean, the event is memory protection violation, and that will trigger a specific interrupt, because each event is associated with an interrupt. And once this interrupt is received by the operating system, the operating system will take some specific actions. Okay. The other kind of software interrupt or program interrupt is a software interrupt instruction. I can use some specific software instruction to trigger an interrupt. Okay, these are soft interrupts kind of thing. And one such example is a software system call. So the system call I have got one slide for that. The system call is also implemented as if it is a software interrupt. Okay, and as you can see here, these are the instructions. Like int is a Intel x86 processors, they use int instruction. It's a software instruction, software interrupt instruction, which can be used to trigger an interrupt. So if I write int say 13 hex, that means I'm trying to trigger interrupt, say interrupt 20, interrupt 19 actually. If it starts from 0, it's the 20th interrupt. ARM processors, they have SWI, software interrupt, this specific instruction. So this low-level instruction provided by the processors can be used by the operating system, can be provided by the operating system to generate software interrupts. Trap in Motorola and syscall in this. So it's a the exact system, the exact instruction, the software instruction is dependent on the processor itself, but different processors do have this facility. And another point is these interrupts are assigned some codes, and if you write that say int space that code, that particular interrupt will be triggered. So this system calls, what is the purpose? The purpose of the system calls is again, if you want to access the disk or for some file access, if you want to go for some additional memory allocation in the RAM, or if you want to access the keyboard like the scanf, when I call the scanf or the printf. So every time I would like to have access to the system resources, which is not allowed to be accessed normally in the user mode, I would like to make a system call. So the operating system provides say an interface. It will have a list of system calls, and through the system calls you can make the request to the OS, and the OS will check if it's a valid request, it will allow, and through that you can. So the system calls are some kind of interface provided by the operating system, allowing access to the system resources for the user processes. Okay, so this program interrupt is sometimes called, also known as trap or exception. Exception because you see, I mean, this is a kind of this something exceptional condition that is not, you cannot predict it when it happens and how it happens, but if it happens, it's an exception. It is not a normal outcome that you expect, and or it can be also called as trap. So trap or exception are program generated interrupts in OS, which is due to some specific events as stated or as specified by the designer. Okay, so this is a follow-up slide on the interrupts. So we have got few more things to understand. So interrupt code, as we mentioned, interrupt code. Now there is a list of finite events that the designer foresees that these events might occur, assigns a particular interrupt for that, and to distinguish between interrupts, it will come up with a particular code, interrupt code, to distinguish between different interrupts or events. So these are hardware set. The hardware sets the interrupt code. So this is defined by the, if it's a hardware interrupt, so this is defined by the hardware itself in the IC field of the PSW. So if you can recall that IC field, this IC field. Okay. So this will be storing the interrupt code. Indicates which specific interrupt within the class of interrupts has occurred. Useful to know the cause. So this node, from this, if you can decode, I mean the users cannot see, but the OS can check that and find out that what is the reason for this interrupt, or I mean what is the event which has triggered the interrupt. And some of the ideas of how the codes are, how these interrupt codes are generated for the IO interrupts. The interrupt code is typically the address of the IO device. So generally, IO devices are also given some unique addresses, and that is interpreted as a IO interrupt code. It assigns distinct codes for exceptional conditions like overflow, memory protection, violation, and all this. So the OS designer identifies, say for example, say 20 exceptional conditions, and for each of them it will define a particular interrupt code. For the software interrupts, it may have a set of 256 interrupts defined, and then each will serve a specific purpose. Okay, software interrupt means the system calls. The system calls. Okay. Now, once the interrupt code is known, which is unique for every interrupt or event, then interrupt masking. What is interrupt masking? That sometimes, although you have got the facility to generate interrupts, maybe all the interrupts, the user processes can generate through the invocation of interrupt instruction. I mean, interrupt software interrupt instruction. But sometimes the process or the OS might set the mask, might prohibit some interrupts to occur at some point of time. Even the programmer can also do that. So you can set the interrupt mask and allowing some interrupts or forcing some interrupts not to occur, sorry, not it's not to occur, but not to be handled during that time. So you have no control over occurrence of the interrupts, because interrupts occurs because of some events. But through this masking process, you can ensure that even though they occur, I ignore it. So it's something like I set my mobile phone in a silent mode. So if somebody calls me and says that, okay, I have got something to discuss right now, while taking the class, I would set it. I would set that interrupt in a masking masked. So if it is masked, so I just ignore it. I don't look into it, and I continue with the discussion. So masks are set by the users or by the OS itself. And setting a mask does not mean that it will not be addressed or not be say handled at all. The point is, maybe at some later point of time after the class, I can switch to the general mode, and then I'll find that, okay, these are the persons who called me. I can give them a call. So the action here is you give a call back, but once it is unmasked, only then it will be handled. So if an interrupt is masked, does not mean that it will be lost. It will be saved, and later point of time, if there is if that is unmasked, it will be served. Okay. Now let us come to the, and this interrupt mask field is also a part of PSW. So when the program is running, the process is running, in the PSW we have got a bit specific, you have got a mask, interrupt mask, and the mask can be specified in various ways. One is if we say 50. So 50 means you might intend to say that all the interrupts which is having a priority or having a number less than 50 will be addressed. Above 50 will not be addressed. Or you might have a a bit vector corresponding to each interrupt, where if it is set to 1 means all those are masked. The rest with 0 will be acted on. Okay. So finally we come to the interrupt action. So what is the interrupt action? So first of all, let us see that how the process knows, or how the OS knows that an interrupt has occurred, and when it knows. So if you look into the instruction execution cycle, so a process means it is executing instructions one after the other. So in instruction execution cycle, there are 4 phases. One, this is second, this is third, and this is the fourth phase. So it is first is you fetch the instruction from the RAM, you decode it, know that what instruction it is, you then execute it, and after it is executed in the instruction cycle, in the microprocessor class, this has been detailed, the timing diagram and all. There is the interrupt check phase. We check for the interrupt line. Okay, so if you find, in the processor, the interrupt line is set, that means some interrupt has occurred, and then that means after every instruction, because in between an instruction you cannot do anything, and instruction time is too small. So after every instruction, you have got to check for the interrupt. If there is an interrupt that has occurred, now it will try to decode the code, IC, the interrupt code, and if it finds that it is not masked, then it will be served. So if an interrupt has occurred, the CPU performs interrupt action, and what it actually does, this is again the schematic I have copied from that Dhamdere book. So what it says that this is the CPU, the PSW. So if after a particular instruction, if it finds that interrupt line is on, I mean there is a certain interrupt that has occurred, so we'll check the interrupt service code, interrupt code, and each interrupt has got a service routine. Service routine means it's just like a function that need to be executed. So it is better known as interrupt service routine, ISR. And there is a vector that is maintained. It's the interrupt vector area. So this vector is nothing but an uh, array of entries corresponding to each interrupt that has been defined in the system. So if the system has got say 256 or say 1024 interrupts, so there will be one entry corresponding to each interrupt. Okay, and in each of these entry, it will have a link to the interrupt service routine. So this IC probably it has got a number which matches with this value here. Okay, and then here it will have some pointer to the interrupt service routine ISR. And this interrupt has got its own some other service routine like that. So whenever an interrupt occurs after every instruction, after checking it, if it finds something, we'll go here, and if it first of all it finds that if it is okay, ignore it. Okay, so this is so if it occurs, then it finds that if it is not in a masked mode, unmasked, then it will go into the interrupt vector. There is area. It will match with the number, jump to the ISR, and it will try to execute. But the point is, you are executing one process. The process is not yet completed. Okay, not even the timer has elapsed. So I'm taking the class. I know that I can take the class for 1 hour. Now there's an interrupt that comes. There's a message from the or somebody came and told me that okay, that there is a very emergency meeting called by the HOD. So even in between the class, so what I do every say maybe after every 1 minute, like the instruction, after every 1 minute, I just look into the door if somebody is interrupting me or something like that. So if somebody interrupts me, and if I find it need to be execute, it need to be addressed, I just stop the class and I go to the HOD's meeting. So before I stop the class and go to the meeting, what I need to do, I need to save the status of my class. Okay, I need to save the status of my class, and then I go and start the interrupt. I mean, go to the meeting, and probably if I've got some time, I can come back and resume the class. Okay, this is what is done. First is it will check the interrupt code, then it will, if it is unmasked, it will save the PSW, the entire state of the CPU in some place. We are not specifying where. Then this contents of the interrupt vector is copied here, and the format is somewhat similar to that PSW. And from here, after it is loaded here, the interrupt service routine is actually triggered. So all the instructions written in the service routine will be executed. And once it is completed, then again so it depends on the policy. If the policy is the process which was getting executed prior to the interrupt will be loaded, that then this will be again loaded back. Otherwise, some other process like that. So the taking action of the interrupt is pretty simple. A vector is maintained corresponding to each interrupt that is defined in the system, corresponding to each event, which points to a service routine for that. And typically, the action may be ignored. I mean, sometimes, like this, I get a phone call, I just ignore it. So sometimes it may happen that for some particular events, you simply set ignore it. There is no execution at all. Okay. So here, as it says that set the interrupt code, save the PSW of the running process, and then load the interrupt vector. And then once it is done, you then think of loading the PSW of some other process or the same process. And what are the contents of the interrupt vector? It contains the address of the ISR. So each of these will have the address of the ISR, interrupt mask, Interrupt mask means see, when the process was running, the process has got its own mask. There's a default mask. But when the process triggered this, when an interrupt came, when the interrupt is executing, the interrupt might have a different set of masks, because it might say that, okay, I do not want to get interrupted by these other interrupts. Okay, so there's an interrupt mask which is to be supported,
Sir?
which is to be supported.
Hello, sir.
Uh,
So
yes.
PS sir asked me to tell you that he has a class from 5:15, so
Okay. Okay. Let me finish this last slide. Yeah. We have got a class right now.
yes, sir.
Okay. And there's a bit that indicates whether it is in the user or kernel mode. Okay. These two slides I'll consider in the next class along with the evolution. Okay. So if you have got any queries, you can put it in that message box. I'll respond to it maybe in the next class, because okay.